So the reason that I brought up specifically this process of rationalizing denominators is because we're going to do it a little bit more today, and I think that's going to lead nicely into talking about complex numbers, which we will cover just a little bit of in this class. We won't go into full complex analysis or anything like that, but we'll talk a little bit about complex numbers. So the first idea that we want to learn is something called a conjugate. So the conjugate, specifically of addition of two numbers, is subtraction. So if this is what I'm given, the conjugate is just me subtracting the numbers instead. So conjugation is just flipping the sign in between two things. It's very straightforward, and how does this make anything useful? Well, take for instance, I'm working with the problem 1 over 1 plus the square root of 2. Now, when we were rationalizing denominators, we just multiplied by what was on the denominator. But that here isn't going to cancel anything out. I'll still have a 2 square root of 2 on the bottom, which is irrational. So I'm instead going to multiply by 1, again in another creative way. But I'm instead going to multiply by the conjugate over the conjugate. So I'm going to multiply by 1 minus root 2 over 1 minus root 2. Again, does multiplying by this change the value of this? No. Multiplying by 1 doesn't change anything. I erased it, but I had set it up there. And I'm just multiplying by 1 in a special way. That's what a lot of creative algebra is, either adding 0 or multiplying by 1 in special ways. So we're doing that here. I can then just multiply across because this is just multiplication of fractions. 1 times this is just 1 minus the square root of 2. And then one thing that you might remember is when I multiply a plus b times a minus b, I get a squared minus b squared. This is difference of squares. This is also useful for factoring things, is difference of squares. So I've got a plus b times a minus b. It's going to be difference of squares. This is going to be 1 squared minus the square root of 2 squared. That's 1 minus root 2 on the top. I haven't touched that yet. 1 squared is 1. The square root of 2 squared is 2. So now I have a completely rational denominator, which is what I wanted to take care of. I wanted to get rid of this irrational denominator. And then 1 minus 2 is negative 1. So I get 1 minus root 2 over negative 1. And then if I want to clean this up just a little bit more, I can get rid of this negative sign by swapping the multiplication or the subtraction up top. Or just multiplying by negative 1 over 1, but this simplifies to root 2 minus 1. Right? The negative sign, it doesn't matter if it's on the bottom or the top. Now if I do negative of 1 minus root 2, that's negative 1 minus minus is plus root 2, which is root 2 minus 1. So that's just something else useful to remember. If I take a negative sign in front of subtraction, it flips the order of subtraction. Any questions about this? The important, yes?
Can you explain about the square root of 2 mentioned?
I have this negative sign here. This is the same thing as if I just put the negative sign outside. or if I put the negative sign in front of the top. Because I have a negative sign in front of subtraction, I can flip the subtraction around. So I get -2 minus 1 instead. The important thing to take away from this example, though, is that if I have something like this in the denominator, to get rid of it, I have to multiply by the conjugate. Any questions about this? I'll do a couple more examples so get a little used to it, and then we will do complex numbers where we will revisit conjugation but with complex numbers. Let's take this far away. Say for example, I have 12x over 2 plus 3 square root of x. And I want to rationalize that denominator. Hopefully this example works out nicely. I just came up with it in my head. So first I want to identify what is the conjugate of this. Remember, that's just swapping addition for subtraction. So the conjugate of the denominator is 2 minus 3 root x. So I'm going to multiply by this over itself, which is always 1. 2 minus 3 root x. 2 minus 3 root x. And then I can multiply everything out. Does everyone have this over here written down? I'll give you just a second. Is anyone confused where this is coming from, though? This is just a clever trick to multiply by 1 in a way that helps us out. Again, like I said, a lot of algebra will be doing that. Multiplying by 1 or adding 0 in a very special way that helps us get somewhere. Okay. So now I can multiply across on the top and the bottom. 12x times 2 is 24x. 12x times -3 root x is minus 36x root x, which that combines. That's x times x to the 1/2. And what is the rule about multiplying common bases with exponents? What can I do with the exponents? Add them. So this is x to the 3/2. I'll put that back in a minute. The bottom, a plus b times a minus b is a squared minus b squared. So a is 2, 2 squared minus b is this, 3 root x squared. All right, so that's 24x minus 36, x to the 3/2, over 4 minus, I need to square both things in here. 3 squared is 9, and square root of x squared is x. And that's what we're left with here. Does that factor out more? See, that times 6 is 4, that times 6 is 6. No, it doesn't work out, but that's fine. And then this would be my final form right here. I don't have a radical in the bottom, and that's what I was concerned with. I just don't want to have square roots in the bottom of my denominators. Like, this looks bad. This is good. This also helps us to evaluate things in the future when we have to evaluate limits and stuff like that in calculus. you want it in this form instead of that form. Are there any questions about any part of this example? This example combined a couple of things together, like distributing a exponent into a product, or combining exponents through multiplication, and then they also had the conjugate there. So are there any questions about anything here? Any questions at all? All right. So that's it for rationalization. I'm going to get rid of this for right now. And we're now going to talk about complex numbers. So we'll start this by asking a kind of simple question. What are the solutions to x squared plus 1 equals 0? How would we solve this equation? It looks really simple, so it should be the case that we have a simple solution. Well, I can very simply just subtract 1 from both sides, but then I get x squared equals -1, and if I try to solve this, I get x equals plus or minus the square root of -1. And can I have the square root of a negative number? No. So we introduce something called the imaginary unit. We write I, this is the imaginary unit. And it is the number such that I squared equals -1. Or I equals the square root of -1. Who has ever seen this before? Okay, so most everyone has at least seen a complex number before. Does everyone have this example all written down? Again, if you're worried about getting everything written down, it's in the lecture recordings and will eventually be in the typed up notes whenever I pick up my Slack and type the rest of them up. But I've been busy reading my own stuff. All right. In general, if I want to talk about a complex number, I have two parts. I have the real part, A, plus the imaginary part. Which is some number times the imaginary unit, times the square root of -1. So every complex number, which we'll say z maybe, is equal to the sum of a real part and a complex part. Both A and B here are real numbers. So some examples of complex numbers might be 2 plus 3i, or maybe 17 minus 5i. That's supposed to be a 5, it looks like an S. These are one number which has two parts. It's a little weird to think about, right? This looks like two separate numbers that we're just adding or subtracting, but it really is just one number and it has two parts. Further along, we'll talk about complex numbers as being points on a complex plane. Maybe, you might see that in trig. But each point has some sort of basically like an x value and a y value. So maybe this point right here is 2 plus 3i. I have my real part and then my complex part. And so each individual number is a point on a two-dimensional plane, which is really weird to think about, but this helps us to solve certain problems. For example, now I have a solution to this quadratic equation, which I didn't have a solution to beforehand. It actually has two solutions. Figured it would. We have operations in between complex numbers, just like we have operations in between real numbers, but they're a little funky. One thing I want to highlight is what happens if I square or cube or take to the fourth power I itself. So I to the 1 is just I, right? Anything to the first power is itself. If I multiply by I, which means squaring, I get I squared, which I said was negative 1. If I then multiply by I again, I times negative 1 is just negative I. So I cubed equals negative I. I can multiply one more time, so times I again. Negative I times I, so I to the fourth is equal to 1. And 1 times I gets me back to I. So I does this pattern of looping around. Right, this is kind of like negative 1. Right, I get negative 1. If I multiply by negative 1, I get 1. If I multiply by negative 1 again, I get negative 1. So it just loops around on itself twice. This one loops around on itself 4 times. So I is a little special with that. This will be useful for when we're going to take, powers or do multiplication or anything like that when it comes to complex numbers. So now we can talk about the basic operations of complex numbers. First with addition. If I add two complex numbers, maybe I have z equals a plus bi and w equals c plus di. These are just two complex numbers. If I want to add them, z plus w, that's a plus bi plus c plus di, which is a plus c plus, I can put that together, b plus d times I. So when I add complex numbers, I add the real part, so this is the real part, and I add the imaginary part. It's a little bit weird, but it's just combining like terms. I have two things that are not multiplied by I. Those go together to maintain being my real part. And I have two things that are multiplied by I, which go together to be my imaginary part. So I just get another complex number with a real part and an imaginary part. For example, if I want to do maybe z equals 2 plus 5i, needs to be a 5, and w equals 3 minus 4i, then z plus w, I add the real parts, 2 plus 3 equals 5, plus I add the imaginary parts, 5 minus 4 is 1i. It's almost like we're treating I like a variable, and it kind of is, but we have a special rule with it that it squares to negative 1. Any questions about this? I know this is weird. This is weird stuff. We're really used to regular numbers, and this is a whole different game. So any questions about this at all? are more than welcome.
So is that the final answer?
This is the final answer.
Okay.
And this is itself another complex number. It's a number that has a real part and an imaginary part. And that's all we do with it. Any other questions? Cool. Subtraction works the same way. So we just subtract the real and imaginary parts. So z minus w, the same z and w, would be a minus b plus c minus d times I. Oh, not a minus b. A minus c, b minus d. My apologies. These are the real parts. A and c are the real parts. And then b and d are the imaginary parts. So we just subtract them with each other specifically. We always keep all the real parts together, and then always keep all the imaginary parts together. It's just like if you're adding coordinate points. Right, if I want to add the points 2, 3, and maybe 4, 1, I add the x parts, and I add the y parts separately. I'm doing the exact same thing here. I'm adding the imaginary part, or the real parts, and then I'm adding the imaginary parts separately. Subtracting the real parts, and then subtracting the imaginary parts separately. Yes?
What would be the point of an imaginary number? Can you use it like a real problem?
Yes, so some real practical examples of imaginary numbers happen a lot of times in electrical engineering. When we're doing wave analysis, we can talk about sinusoidal waves, right? If you're talking about alternating current, for example, this can be modeled very, very efficiently with complex numbers, which we typically use as e to the I theta. We start talking about them as rotations instead. And so we can represent really complicated problems using this. There are also things in calculus, problems that we wouldn't be able to do in real numbers. If we rewrite them in terms of complex numbers, the solution is really easy. So most of y'all probably will never have an application for this unless you plan on going into physics, engineering, or mathematics. But if you plan on going into any one of those fields, you'll see complex numbers pretty frequently, actually. Or at least if you're going into mechanical engineering, computer engineering, electrical engineering, something like that. Cool. The other reason is because it gives us solutions to polynomials that we didn't have solutions for. So for example, the polynomial x squared plus 1 equals 0, there are two solutions for this, but neither of them are real. The solutions are plus and minus I. Or in general, anytime that we have, right, remember with the quadratic formula, x equals negative b plus or minus the square root b squared minus 4ac over 2a. If this chunk right here, which we call the discriminant, if it's negative, our solutions are complex. Specifically, we will talk about this with what's called the fundamental theorem of algebra. We cannot have the solution to every polynomial written with real coefficients unless we include complex numbers. This is an example of that. This has real coefficients, right, 1 and 1, but it has only imaginary solutions. So then we have to start talking about imaginary numbers. It also is like, if we go to factor something, sometimes factoring includes that. Like one way that we can factor a squared plus b squared, instead of a squared minus b squared, a plus bi times a minus bi. We could factor it like that, and then deal with the individual factors if we needed to. So we're used to difference of squares. This is how to factor sum of squares, which we might look at a couple of examples on down the road. Any other questions? That's a good question. Hopefully that somewhat answered your question. The main reason though, and this is the one I always say, electrical engineering uses it quite often. When you're doing like time series analysis with waves or anything like that, or voltage. Voltage, when you start talking about the time difference in voltage, you have to have complex units. Any other questions? If you are going into math, physics, engineering, computer science, anything like that, I do recommend just taking a couple minutes and looking up how complex numbers apply to your field, because you do use them quite often, especially programming in computer science. Imaginary numbers are actually used very often for coding physics engines and doing robotic vision. So if you're interested in trying to program robots to see and map out an environment, it uses complex numbers as well, which is really interesting. So there's addition and subtraction. Multiplication is a little weird. We'll see that one. So if I want to multiply two complex numbers, again, I'm just in general stating this, that's why I'm using letters instead of numbers. For any general two things, I can use this. I just FOIL it out. I get A times C, A times DI, BI times C, and then BI times DI. AC I can leave by itself. Yeah, I'll leave it by itself for now. And then I have AD with an I and BC with an I. So I can just pull the I outside. This is going to be my imaginary part of the solution. And then what happens if I multiply I with I get -1, so I get minus BD. So I have another real part. I can put it with my original real part. I get AC minus BD plus AD plus BC I. Here's my real part, and here's my imaginary part.
I don't know what parts you really multiply by imaginary.
Imaginary is always multiplied by I. The real part is what's not multiplied by I.
What was it about, like, for the other one? Before that, you said you can move the negative B.
Because this has I with it, it's AD times I.
Oh,
This has I with it, it's BC times I.
I didn't see.
Any other questions? Alright. So we'll look at an example, a straightforward example. Let's do 3 minus 2i times 1 plus 4i. 3 times 1 is 3. 3 times 4i is 4i. Negative 2i times 1 is minus 2i. Negative 2i times 4i is negative 8i squared, which is positive 8, because I squared is negative 1. I put my real stuff together. That's 3 and 8, which is 11. And my imaginary stuff together. 4 minus 2 is 2. And then if I break it down, this 11 should be AC minus BD. 3 times 1 is 3, minus negative 2 times 4. So minus negative 8 is plus 8. 3 plus 8 is 11. That works out. And the next one, AD plus BC. 3 times 4 is 12, minus, oh, did I mess something up? I don't think I did AD plus BC. let's see, that's 3, 12. Oh, that's 12i. Why did I put 4i? That's 12i and that's 10i. My apologies. I make silly little arithmetic mistakes all the time, so I apologize for that. So 3 times 4 is 12, minus 2 is 10. So it works out the same way as well. Any questions about complex multiplication? All right. Division is different, right? We can't just do division by, regular division, right? With real numbers, I can just do 3 divided by 4, and I get an answer. But complex numbers, there's addition and addition on the top and the bottom. So we're going to do something very similar to rationalization, where we take the square root of the denominator, or we're going to multiply by complex conjugates instead. So a regular number, I'll put over here. A regular complex number is a plus bi. The conjugate of that is we always make the imaginary part negative. A minus bi. So for example, what's the conjugate of this number? 11 minus 10i. I make the imaginary part negative. So if I go to do a problem with complex division, for example, if I want to do 3 plus 2i divided by 1 plus 4i, I want to try to get this complex stuff out of the denominator, so I'm going to multiply by the denominator's complex conjugate over itself, just like we did with rationalization. What I mean here is I take the conjugate, that's going to be 1 minus 4i, and then I multiply 1 minus 4i over 1 minus 4i. Does doing this change the value of this? No, I've multiplied by 1. I keep asking all that question because it's important to recognize that doesn't change anything. And then I just multiply out using my complex multiplication. 3 times 1 is 3. 3 times negative 4 is minus 12, and there's an I there. 2i times 1 is 2i. And 2 times negative 4 is negative 8, but I squared is negative 1, so I get a plus 8. I accidentally picked the exact same examples over there, that's kind of funny. Oh, I didn't even realize I picked the exact same one. When I make up problems in my head, I always pick the exact same numbers for some reason. 1 times 1 is 1. 1 times negative 4i is negative 4i. 1 times 4i is plus 4i. 4i times negative 4i is negative 16i squared. I squared is negative 1, so I get plus 16. Let's see, I've got 3 plus 8, which is 11. Negative 12 plus 2 is 10i. Oh, there's a negative there. On the bottom, I have negative 4i and 4i cancel each other. They just go to 0. And 1 plus 16 is 17. If I want to write this now as strictly a real and complex part, I got 11 over 17 minus 10 over 17i. Right, if I have the same denominator for my fraction, I can split it into the 2 different fractions. So that's what I've done here. What we notice on the bottom is that this complex stuff canceled out, and that's exactly why we're using the complex conjugate. I wrote earlier that the sum of squares is kind of written like this. That's exactly what I get. I get 1 squared plus 4 squared, which is 1 squared plus 16, 17. In general, a plus bi times a minus bi equals a squared plus b squared, which is what I wrote beforehand. So the product of the number with its complex conjugate is the sum of the squares of the parts. That's just how to say in words what I've written here. One thing to note is that there's some notation that you'll see for taking complex conjugates. There's 2 different ways people write it. If z equals a plus bi, the first way to write it is I put a bar on top of my z. And this means take the conjugate. The other way to write it, which is how I typically write it, is I put a star above it. And this also means take the conjugate. So you can use whichever notation you want. Engineers use this. Engineers and physicists typically use this notation. Mathematicians use this notation a lot more. So if you're doing something in the future and you see complex numbers, you'll see one of these versions of notation. More than likely you'll see this one, but I use this one a lot. So I just wanted to show it to you in case I use it. I don't want you to be confused. Yes? Yes. So if your homework says write it in the form a plus bi, this is not in the form a plus bi. This is a fraction of things. I want to split it up into my a, my real part, and my bi, my imaginary part. Good question. Any other questions? Any questions about complex numbers as a whole? All right. That wraps up everything that will be on the first homework. That first homework is due Sunday night. I think I'm probably going to push back that due date so that you don't have to do it all over the weekend. So I think I'm going to push that due date probably to Wednesday, I think. Give y'all a couple more days on it, and also give y'all a couple of days to come to my office hours if you have questions. Yes?
For the tips on it, if we get more tips, can we get more, or it's like a set number?
I think it's a set number. I need to go in and check that. So I will go in and check that. If it's a low number of attempts, I'll bump it up so that y'all have plenty of attempts to do it. Yes? Huh? It's 5 attempts? I'm going to bump it up to like 100 or something so that it's essentially unlimited attempts. And so you don't stress yourself. You've gone through 4 attempts, you don't get it, and then you're like, okay, ChatGPT is going to have to come in here. I want y'all to be able to actually do it as many times as you need to figure out the problem.